If there is one thing that I would like, if I could sort of wear on a t-shirt and wave as a banner, it's the ocean is not a blank slate. It's a living, it's the equivalent, it's got the complexity of a living organism. So treat it like that.
Do you wake up in the middle of the night screaming because the AMOC is going to shut down?
The big deal in climate science circles is that this is even on the table. It's so serious if it happens. I mean, we really are talking about fundamentally changing what the planet looks like. So I don't worry about it happening, but I am worried that it's even on the table.
Hello, I'm Michael Liebreich, and this is Cleaning Up. Our planet is called the Blue Planet, not because it's depressed about the stuff that's being done on or to it, although you could understand that, but because 71% of its surface is covered with oceans, and they show up blue from space. The oceans define every aspect of our planet's physical systems and its ecosystems and human history and human culture. The oceans also define the planet's future. They're absorbing 1/3 of all the excess CO2 we are recklessly pumping into the atmosphere, as well as 90% of the heat. If that were ever to stop, we would be in a planet's worth of trouble. Oceans also represent an almost unexplored frontier in the fight against climate change. Whether as a host for offshore wind farms, an enhanced carbon sink, a source for critical minerals, or a route for high voltage DC cables. But could there be unintended consequences? I'm used to having guests on Cleaning Up whose expertise is a mile wide and an inch deep, or an inch wide and a mile deep. But my guest today has expertise which is 25,000 miles wide around the circumference of the planet and up to 7 miles deep in the Mariana Trench. Professor Helen Czerski is a physicist and oceanographer. She's also Associate Professor in the Department of Mechanical Engineering at University College London, and author of 2 books, A Storm in a Teacup and The Blue Machine, about the physics of the oceans. That's what we're going to be talking about today. Please welcome Helen Czerski to Cleaning Up. Helen, thank you so much for joining us here today on Cleaning Up.
Thank you for having me here.
So we always start by asking people the short version, sort of 30-second version of who you are and what you do.
I'm really hard to label, but I am an associate professor at University College London. I study the physics of the ocean, and I'm also a writer and broadcaster. So I do lots of different things, but all of them concerned with getting physics and thinking about how the planet works into, other people's minds, sharing that with the public.
Bubbles. Am I right?
I'm a bubble physicist, and it is a real job. I study the bubbles in the upper ocean. And it's interesting because bubbles are, I will spare you the full bubble rant, but bubbles are interesting because they're a liquid and a gas trying not to mix. And together, this pocket of gas inside a liquid, so I'm talking about underwater bubbles, not soap bubbles, can do things that neither a liquid or a gas can do. So it's a really interesting thing to study, and there are lots of them in the ocean. Did
everybody get that? Bubble wrap? I thought I would just underline it because we're obviously into, you've done this before, right?
Well, I have spoken about bubbles a lot. Well, it's interesting because it's one of those things where people sort of don't take it seriously. It's almost like the Ig Nobel Prizes. They make people laugh and then make they think. I'm not saying I deserve an Ig Nobel Prize, but it's that thing where people go, they associate it with play, with bubbles in the bath and dolphins and fun things and sort of trivia. And then once you get into, where bubbles are and how much they influence all kinds of things, then it starts to look a lot more serious, and then people get interested.
So how did you get interested though? Because most people, their first experience of the ocean is, do you remember the first time that you saw the sea?
Listen, mate, I come from the north. What we had there is 2 seas. We've got the North Sea and the Irish Sea, and they're both cold and horrid as far as a 5-year-old child is concerned. So when I was growing up, my association with the sea was generally that it was grey and it had seaweed in it and slimy things. And I was, I didn't go very often. It's not that I had a sort of deprived childhood, but the sea didn't feature very largely because no one had told me about the ocean. And so I did, I went to Cambridge, I studied physics, became an experimental physicist, went through a whole PhD studying explosives, slightly accidentally, but I was good at building the experiments, like high-speed photography and ways of looking at small things happening really quickly. And I liked that challenge. but I didn't want to blow things up. And then after I finished my PhD, I then went looking for something that involved small things happening very quickly that wasn't blowing things up. And after a while, I came around to bubbles because, of course, they're formed and they rise and they burst and they do things just too quickly to see. So you can use high-speed photography. And so I wound up very accidentally at the Scripps Institution of Oceanography because a guy there studied bubbles. And that was my introduction to the world of bubbles. And I was useful in that lab. I understood because it was, tanks and pipes and oscilloscopes, and I got all of that. And then there was this kind of big frame near the door, this sort of 2 meter high, large cube. And I hadn't really looked at it. And one day they opened the door and they carried this thing down and put it in the ocean. And I realized it was their eyes and ears into another world. And even though at that point I'd been at one of the world's greatest institutions of oceanography for 3 or 4 weeks, I hadn't really looked at the ocean. And as soon as I looked with a physicist's eyes, I got it. There's a story here. There's a thing to study. And no one had told me about it. And I was so indignant. Like, how can you not talk about that? So I became an oceanographer by the back door.
And so at that point, you've done your PhD already.
Yeah.
By the way, I loved blowing things up. I did a bit of that at Cambridge. Spalling, so bits of chalk, and then you put an explosive cap at one end, and then it slices itself into. So
that's right.
Well, how could you not want to spend the rest of your life doing that?
2 reasons. First of all, there's a lot of clearing up. And secondly, it's kind of it doesn't really get you anywhere. Like it's a sort of, unless you are keen on blowing things up for destructive purposes, which I'm not, it sort of doesn't go anywhere.
No, but there's a lot of industry that would also have had high-speed photography. I mean, there's all sorts of floating bed, combustion processors, and hopefully we're getting rid of those. We'll get onto that. But there are things in industry that would have been closer to home than going over to Scripps. Yeah,
well, there was a lot of interesting solid-state physics. I mean, that's the reason I was doing it. I was doing it because actually, when you get the materials that blow up, I mean, explosives are mostly solids. And they're quite complex solids, but they have this weird property that if one part of them gets to a particularly high pressure and temperature, that goes pop, and then the whole thing goes pop. So that's quite an interesting diagnostic. So you can study how materials operate by when they go pop. But it just felt like, it was too close to the defense industry for me, and it was too inward looking, and I wanted to look outwards.
Aerogels.
I mean, I had a friend who made a very interesting type of aerogel at Los Alamos. I also worked at Los Alamos for a bit during my PhD in the explosives division.
More stuff blowing up.
More stuff blowing up. Although they wouldn't let me. Well, they wouldn't let me in to see the really big stuff because at Los Alamos there's inside the fence and outside the fence. And if you're a UK national, unless you've gone through years and years of vetting, you're never allowed inside the fence. So my lab was outside the fence, where there were big labs, but you weren't allowed into whether. There was a day where every explosives lab has this, but. You don't want to keep explosives lying around if you're not using them. So once a year you have to dispose of them. So how do you dispose of explosives, right? You blow them up. So they have a day. I mean, I assume they still do it, where they kind of take all the leftover bits and pieces that haven't been used, and you basically put them on a big bonfire, stand well back, and chuck in a match. I mean, it's not quite that primitive anymore, but it's that kind of idea. When I finished my PhD, there was a day where we all went to a sort of off-site, and you got rid of the rest of your samples because it's the only way to dispose of them safely. Anyway, I wasn't allowed to see that at Los Alamos. But I just wasn't there were all these interesting things in the world, and it just felt inward looking. And I had kept trying to find the physics of the natural world. Before I sort of thought about doing geology, and but I couldn't find a way in because it didn't have enough physics. And then bubbles had enough physics, and then I was in.
And I mean, you've really, I don't know how to say this, but you've been in your element ever since, right? So, but the purpose of the conversation sort of up to this point is you're a really hardcore scientist, because if you read the book, it's beautifully written, by the way. And I don't say that often to people. It's really, really well written. But a lot of it is not physics. There's a small amount of physics. There's a lot of interpretation of physics. There's an awful lot of sort of culture and history and a bit of philosophizing as well.
Well, yeah. So the thing about all of that is there's a skeleton of physics in it. I mean, if you look at the structure of it, it's kind of a physical oceanography textbook. The first, half of the introductory
when I said a little bit, I didn't mean to dismiss it. I just said that it's kind of the. It's
but
like
why
the
do
iceberg.
we care? We care because of what it means, and we care because of the influence it has on us. And when you think of it, the thing that I'm talking about in the book is that the ocean is this gigantic liquid engine. It is doing things. It's not this kind of passive pond that everyone thinks. But one of the, and no one's really written a physical oceanography popular textbook, a popular science book. And I think one of the reasons for that is that it looks like it's just water. It's kind of water and more water and other water. And so the reaction is, why should I care? But once you start talking about the impact that it has on culture and on history and on animals and on us, then people have a reason to care. So it really sort of, I could see that connection. For years and years, people would say, why do you care about the ocean? And I would sort of struggle because you can't say it all in 1 or 2 sentences. And I knew this richness was there, but no one was quite making that connection.
But you didn't just say, because it's got bubbles in it.
No. No.
Simple version.
Well, it is, but the bubbles are literally superficial. They're almost all up at the surface. But this business of it being this 3-dimensional engine, I mean, it really does change how you see the planet. And the fact that we teach, the thing I say in the book is that 50 years ago, there were these Apollo missions, right? We went to the moon. We thought we were going to the moon. Of course we didn't. The most important things from the Apollo missions were looking back at Earth. There's no question about that. And the astronauts at the time said so. We went to the moon to see the Earth. And so we could see we're a blue planet. And then for 50 years, nobody asked any questions of that blue. It's just where the fish live. But this, it's doing stuff. And then you see the planet differently.
So can I try you out on some of what I suspect are your pet hates? Okay, you make a fine argument that fundamentally it's just kind of empty, right? I mean, it's just other, it's just full of water. There's a lot of it, and there can't be that much going on, right?
Anyone watching the video will be seeing me roll my eyes as you intended. No, there is loads going on. And this is where we are arrogant in thinking that our size and our way of seeing the world are the only size and the only way of seeing the world that matters. And the ocean is doing plenty of things. I mean, it sets the scene for the whole of the planet. It's the thing that makes Earth livable, not because it's blue, but because it's a temperature buffer. And it's shunting heat and nutrients and life around all of the time. And those massive shunting processes set the scene for what it's like on land, which sets the scene for what it's like for us. And so we sort of live in the ocean's shadow. And so it is doing things all the time, and it's doing very, very small things that are too small to see, and it's doing very, very big things that are too big to see. And it's doing very fast things and very slow things. And so humans kind of look at it and think, well, it can't be doing anything, because when you look on our size scales and our time scales, we can see a fish, and we quite like the fish. We're quite interested in the whale once in a while, but we don't see anything else. And that's a measure of our blindness.
Dolphins.
Oh yeah, we like dolphins.
We like dolphins.
And bluefin tuna, which are back in British waters, which is a great thing. So, but we privilege our own view, and now we should be able to take a step back, right? Our civilization should be mature enough to take a step back and really see what it is.
I was very struck by one number that you had in there, which is if you go from the smallest phytoplankton to, I think it's the blue whale, you've got, is it 23 orders of magnitude? Yeah. And if you go up to the biggest things you deal with, which are probably currents and the oceans themselves, then presumably it's 26, 27, it's another few orders of magnitude. I mean, that's a lot to get your head around.
Well, it was, and I got that coming in at the start, because when I did my first after I went to Scripps, I went to a bigger physical oceanography department, and everybody there did large scale physical oceanography, and I didn't understand anything they were doing. And I was because I've been doing microscale physics on sort of nanoseconds, and I realized that even then there were sort of 12 orders of magnitude between how they thought about the world and how I thought about the world. And then of course when you look deeper into the ocean, that just gets even bigger. And it is a wonderful thing. So the ocean really is an engine. It's converting heat energy into movement. But it's not like a steam engine where this piston pushes on that thing and the other thing goes around. It's layers. There's all these different structures of engine all happening at the same time, one on top of each other. And the reason it can work is that they're all different sizes and timescales. So there's this beautiful intricacy in what it's doing. And so really part of the reason for the stories in the book is that if you look through a certain lens, you see one of those stories, and then you kind of refocus your telescope or microscope, whichever one it is, and then you see a different story. And so depending on how you look, you see different things, which is wonderful.
Yeah, and you've got great sort of intricacy of these things. So I was struck by the scale range, but also by the structure. So you write about things like when the currents throw off a cold circulating bit and a warm circle. I don't know what they're called. You'll give us
mesoscale eddies.
Mesoscale eddies. I knew that. Well, I do know because just by the way, for that thing, but in the background, as everybody watching and those listening can't see this, but there is a copy of Helen's book behind us here, so mesoscale eddies. But they're really intricate in the way they move. I mean, of course, you can do. Presumably they're microscale eddies you can do in a cup of tea with a spoon. You can create an eddy.
Yeah.
But this is like a lot bigger, but just as structured. And then there's lots of other lovely structures, standing waves that probably led or possibly led Mark Antony's fleet to disaster.
Right.
That just lots of structure, but that nests up and down over all these different scales.
Yeah. And it's because the water to us looks mostly transparent, generally, depending on how much of it you're looking at. It's hard for us to appreciate that just by looking at it. But it is the ocean. The ocean has anatomy. Like it's got different structure in different places, and that's kind of written in temperature and salinity and then chemical composition and nutrients. So there's all these different ways. You can look at maps of the ocean in, for example, phosphorus distribution or nitrogen distribution. Or copper, and you see these different things. So really every part of the ocean has a chemical signature.
And that's really important, that it doesn't fully mix.
Yes.
It's miles from fully mixed. That was news to me, just how unmixed it is, how separate these different bodies of water are and how they remain possibly for thousands of years.
So that is what makes the ocean interesting, is that it is not just that it's not in equilibrium, but it's not fully mixed and it's not fully unmixed. So if it was unmixed, it would just have density layers that were exactly the same and never moved, and nothing would go between them, like one of those cocktails.
Like a cocktail.
They've got
layers.
It would be dead and nothing would go anywhere. And if it was fully mixed, then you don't get any of the structure, right? Because it's just one big pond and it's the same everywhere. But this in-between stage where there's not enough energy to mix it up, because that's what it is. I mean, the ocean is... The question of how energy is distributed in the ocean is actually quite a fundamental one, but a lot of it comes from tidal mixing, for example, and currents. But you need energy to mix things up. If you've got density layers, it takes energy to mix them up. And so we don't have enough energy in the system to fully mix it. But we have these sporadic injections of energy that can mix little bits. And then you've got these features that can move around each other as the Earth spins and as, currents and other things move the water around.
So this is fundamentally a climate podcast and YouTube channel. And so first thing is, most people will probably think of, CO2, which fully mixes in the atmosphere fairly quickly. This is completely different. But also the energy is not just coming from the sun, is it? It's not just the solar radiation. You've also got energy coming in from the moon, and the moon is slowing down. Now that was news to me.
Yeah, the ocean, one of the big differences between the atmosphere and the ocean from a physical point of view is that the atmosphere is heated from below because sunlight comes through the transparent atmosphere, heats up the land, and then that heats up the air from the bottom, right? Which is why it's colder at the top of a mountain. So the atmosphere is heated from the bottom, so you easily get convection and mixing. But the ocean is heated mostly from the top. The sun comes in, it heats the top surface. Water is not actually very transparent to light. It doesn't go very far. So it heats up the top, dumps all the energy there, and then what's underneath doesn't have a direct source of heating. Geothermal energy is negligible for all of this. But what does happen is that the moon is tugging water around. And it's not, there's this picture of the tides that is two bulges just going around. And of course that doesn't happen because the land gets in the way. So it's much more interesting. You get water kind of sloshing around these big ocean basins. But as the moon pulls the water, it can pull it over sort of roughnesses like seamounts and chains of underwater mountains, that kind of thing. And as you force a current through a narrow sort of obstruction, if you like, you dump energy in mixing, but then also that generates waves called internal waves that can be sent out. So inside the layers of the ocean, you can kind of have a wave with it. It's not like a single wave on the top. It's kind of it's a wave that's got some depth as well, but it can travel out and energy can travel out. And then eventually that wave will break. And the breaking can happen over days. and over scales of hundreds of meters, but it does break. And it just in the same way that a breaking wave at the surface kind of mixes in air and water and it mixes everything up, a breaking internal wave mixes everything up. So you've done some mixing. So you've dumped in some mixing energy from the moon. And of course, the moon, you know, as you said, there's, you know, we're not into perpetual motion machines here. So that energy came from the energy within the Earth-Moon orbit. And as a result, the Earth and the moon moving slightly further away from each other. So the moon moves, I can't just remember the number, it's something like a few centimeters a year further away. But we can measure it, and we can measure it because the Apollo missions left mirrors, and we can bounce light off those mirrors and we can see that it is moving further away. So yeah, it is a big source of energy to the ocean. Sadly, not any use as a renewable energy source or anything else, but still there.
So, and eventually all of that lunar energy is also going to end up as heat, but it just does these really interesting things along the way. So that cocktail that's got the layers, it can have waves between layers. It doesn't just have to have a layer on the surface. If you put a spoon in, you can actually mix two layers, but leave the rest unmixed. And it's doing those sorts of things.
That's right. And you can see it, you know, the simple example is that if you get a jar and you sort of put half oil and half water, you get this sort of line between the two, which is a density, you know, it's a difference between two substances, but it's a density thing. And if you swirl the jar, you'll see that boundary swirls.
Lava lamps.
Lava lamps. Yes. Everyone loves a lava lamp. I've got one in my office, actually. I found it the other day and it still works. I used to use it to demonstrate convection to students. But yeah, so you're creating, again, structure, that all these things are happening.
Another thing that's driving structure is salinity. So you talk, I mean, you and I, when we first met, the reason I thought this is fascinating is because you talked about the thermodynamics, the heat flows. And I'm obsessed with trees actually as heat pumps. And so we had that conversation. But actually salinity, I hadn't really thought as much about, although obviously it's a big driver of things like the currents.
Yeah, so salinity matters because it's the other thing that affects density. And over most of the ocean, temperature is the major thing driving what layer a water packet is at. So the temperature is the most important thing. But salinity matters. Salinity is kind of next up. It's the other way around in the Arctic, actually. So underneath the Arctic, in the Arctic Ocean, there's a layer of water which is actually warmer than the surface. But it doesn't float up to the top because it's too salty. So actually there's enough heat to melt all of the Arctic ice already in that buried layer, but it's there, it's staying away from the surface because it's too salty to float upwards.
Up at the surface, it's presumably -2 degrees or something because it's salty water and it's in contact with ice. But down below, it's, what would it be? 3, 4, 5, 6?
Maybe it's not a huge difference. I think it's 2 or 3 or something like that. But it's definitely, you know, water holds a lot of energy.
But in general, down at the bottom, you've got more salty and colder, therefore more dense.
Colder.
And at the top, you've got less salty and warmer, therefore less dense. So it sits. That's why you need energy to mix it.
So the salinity is actually pretty similar, and that's what lets the whole thing circulate. So the fresh water. So you've got a mixture of water and salt. And the salt stays the same, right? But the fresh, you can evaporate or you can put rain in.
Exactly, because I'm thinking it's raining on it, but of course it's also evaporating. Yes. So net, the top surfaces are going to be similar salinity, except somewhere where there's less evaporation.
That's right. So for example, the sort of classic comparison is the Baltic and the Mediterranean. So in the Mediterranean, it's very hot. You've got lots of evaporation. You've got very little river inflow, very little freshwater inflow. So the Mediterranean is very salty. In the Baltic Sea, it rains a lot right now. It's cold rain. You get loads of river input, but you get very little evaporation. And you also get relatively, like the entrance to the Baltic Sea is very narrow, so you don't get much salt in. So the Baltic is relatively fresh. So the salinity matters, but it changes because of what the water is doing, not because of what the salt is doing. The salt's generally very well mixed. So yeah, so salt is important because it drives the circulation. So for example, in the Atlantic, you get lots of evaporation near the equator. So you get warm water and it's salty because there's been lots of evaporation. The circulation kind of carries that warm water northwards and then it cools, but it's also still salty. So then it sinks. And then that takes it down to the bottom, well, some of the way down. And so you have this overturning circulation. So mostly ocean currents move horizontally. Because they stay in their density layers. But if you mess about with the salinity, you can also make them move vertically. And so that's how you get an overturning circulation, which is an oceanographer's word for water going between the levels. So from the top down to the bottom, and then from the bottom back up to the top.
Right. And that is, of course, absolutely critical for climate.
Yes.
Going to get onto that.
Yes.
But before we do, that's the physical reality of the oceans. But you also then talk about, you've got messengers, passengers, and voyagers. And can you give us what are those? What are those categories of things that you talk about in your book?
Right. So you have an ocean that's got an anatomy, and then it's doing things, and then the question is, well, what's traveling through it? And so the messengers, passengers, and voyagers is my way of categorizing everything that travels through the ocean. So the messengers are things like sound and light, which are they can travel without carrying matter, but they carry energy and information. So that's sound and light. So they're the messengers. They just pass through. And then, so the passengers are the things that are carried passively. So that's very tiny bits of life. But also things that are not living. So for example, carbon you talked about, there are, nutrients, all that kind of thing. Those are just, if the current goes that way, they all go that way. So they're just carried around passively. And then the voyagers are the ones that are making an active contribution to their movement. So they are swimming generally, or making themselves float and sink to change their density. So they are actively traveling through water masses to go somewhere in a directed way. Obviously not all of them are conscious, but they choose to go that way, and off they go. And of course that last category includes us. When we are sailing ships across the surface, we are voyagers across the ocean. And the point is that all three of them are affected by the structure. And of course, the structure is what gives them somewhere to go. But it's also what sets what that journey's like. Do they find food on the way? Do they interfere with other things? What the whole business of being, like, if you're going to be a voyager, you need a map, right? So what's the map written in? Well, it's written in the anatomy of the ocean, the structure of the ocean. So there are voyagers that, we think of ourselves as going looking for other land, for example, but even human voyagers do go looking for structures in the ocean without knowing it. So for example, we remember I don't remember, but we know of the cod wars around Iceland. So it's not the case that Iceland just happens to have fish. Iceland is sitting at a crossroads in the ocean where different water masses mix, and it's like a city. And so when all these fishing vessels in Europe are going to Iceland, in the 70s or 80s, whenever it was, to argue over who gets to fish the cod are there because of the structure of the ocean. So the humans are navigating to a specific structure in the ocean because it's got something that they want. And of course, the animals do that too. And
you give a great example of the penguins that live on some island, can't remember its name, but it's miles from everywhere in the South Pacific. And then they take turns, the female and the male, to swim 400 kilometers to where the warm and the cold oceans meet, and in that area of I'm paraphrasing your book. I should let you do this, but they go very intentionally to this divide, which in theory is shifting. I mean, it could be in different places on any given day. So this is what you're describing, a boundary between, in this case, warm and cold water, is called an ocean front, and they are very productive places. They're like it's like a vertical ribbon. Again, like a city in the ocean, because where two water masses mix, it's just like a city. You have a bit of everything, right? If one water mass has a bit less, phosphorus or something, the other bit might have some. So you can do things because you have a bigger supply of whatever you need. So these are very productive areas. There's lots of things growing in them. And if you're a penguin, right, you've got to you're not sort of an albatross that's just going to swan off across the ocean. Albatross off across the ocean, whatever Swanning,
you do.
Not a swan,
Swanning.
albatross.
Albatrossing,
fly across.
Yes. Where you're just going to stay at sea. You've got to get back to your egg. You've got a limited time, and you need to get as much food as possible in a limited time. And so, because otherwise your mate and the chick will starve. And so you can't just go off searching randomly. You need to go to a place in the ocean where you're pretty sure there's going to be food. And so they navigate pretty much, they swim pretty much straight south to where this ocean front is. They'll hang around there feeding for a week, and then they will swim straight back. And the reason they can do it is because the ocean is predictable. So as you say, these features move around a little bit. But the point is the general big pattern is predictable. So they know that if they're going to swim, they're going to get there. And that is one of the reasons why climate change matters, because in the same way that if we shift patterns in the atmosphere, we shift where you can do certain things. If we shift these patterns in the ocean engine, then you have a problem for a species that has only got the capacity to swim 400 kilometers, feed through a week and swim back. If you push that front south, it can't swim 500 kilometers. So you've got a problem.
So I said that your book was beautifully written, and you can tell I've enjoyed it. And I was expecting more of it to be about doom and gloom and climate change. But actually, it's really just the last sort of, you touch on it here and there, but it's really
deliberate.
just the last 30 or 40 pages. But we do need to talk about...
Yeah. That was a deliberate choice. And it wasn't just that climate change is really depressing. It's that I think, and I'm sure you see a lot of this in the climate solutions space, whatever you call that people talk about systems with a very superficial understanding of what they are. And of course, the world's a complex place. Like, we can't know everything about everything. We're all kind of trying to catch up. But if you walked into a room with a doctor and their idea of a human was kind of a stick figure with a smiley face, and that's all they knew about humans, 2 arms, 2 legs and a head, you're not really going to trust that doctor to come up with a sensible solution. And yet, so when you have a system, I think you have to appreciate something about what it is before you go proposing solutions, or before you know how much to worry about it. I think the other thing is that it's not just that you should understand how something works before you go proposing to change it. We also see that people hear headlines about climate change things and, krill in the Southern Ocean have disappeared and all the jellyfish are going to take over, whatever it is. And the problem is, if you don't understand anything about what the ocean is, you don't know what to do with that information other than panic. And panic makes you helpless. Whereas once you show people, first of all, this is a thing and it's an interesting thing, and then you tell them, oh, well, the krill have disappeared, you don't need to tell them that much more because they can already see why it matters. And I think that, we have limited time to come up with decisions about what we're going to do about climate, but the ocean is such a complicated thing and a beautiful thing that I think there's so many proposed solutions in inverted commas that just don't make sense if you understand what it is. But people only look at the superficial bit, and so they go, oh, well, obviously we'll just do this.
So I've now reached, having read your book, I've now reached the one step. What's the step beyond the smiley face and 2 arms and 2 legs? Because the krill disappearing, I'm now this great expert. They disappeared because the whales no longer eat them and then poo near the surface. There's a lot of poo in this book, by the way.
Yeah, people take that. I get teased a lot for it as a physicist for talking about poo. Honestly, it's like, as a physicist, you have to work a bit harder to get people interested. And it is possible. And in biology, in marine biology, everyone loves a dolphin. But it turns out the easy route for physicists is just to talk about poo. Because not only is it important, but it matters because that is the raw material, right? We should think about materials starting with the poo because that's the start of the cycle, not the end of the cycle. Anyway. So yeah, the whales. So the point in the ocean is that because it's a bit slower to distribute things, you don't have the wind to take things long distances very fast. You have to, it's a lot harder to bring things together. And so if you want life, you need both nutrients, which is the raw material, and you need energy, which comes from the sun. So since the sun only gets into the top of the ocean, unless you have nutrients at the top, the ocean is dead. So because of the layered nature of the ocean kind of should be dead, really, because the sun heats the top layer, makes it nice and buoyant, keeps it at the top. For various reasons, nutrients tend to sink. So the nutrients are in the cold water down below. The sunlight and the energy is all up at the top. Never the twain shall meet, dead ocean. Now, the ocean has various ways of breaking that paradox. But one of the interesting ones in the Southern Ocean is that, so the Southern Ocean, the food chain is relatively simple because you have phytoplankton, which are the little sun harvesters, the single cells that take the sun's energy. They get eaten by krill, which are kind of small shrimpy things. And then blue whales eat the krill. I mean, there are other things there, but it's kind of simple in a big picture. And so the thing about the phytoplankton need nutrients. So you grow some phytoplankton at the top, the krill come and eat the phytoplankton, the whales come and eat the krill. But everything is sinking. So when bits of krill and bits of leftover life biology, the nutrients are generally sinking down out of that top layer. So you're getting less and less for the phytoplankton to be made from. And it turns out in this case, one of the ways of recycling nutrients in the ocean back up to the surface is that whales, which blue whales can feed deeper down. So they're eating things at depth. But of course, they're mammals like us. They need to come up to the surface to breathe. So up they come. And when they breathe, they also poo. And they release these very iron-rich plumes of feces into the ocean, which are red because of all the iron. And it brings nutrients back up to the surface so the cycle can start all over again. And so that's the point, is that if you, instead of just hearing, the krill are all dying and then panic, you've got now you can think about it, right? You can see what the impact is. You don't need me to give you a list of all the things. Now you think about the system differently. You're much more likely to make good decisions by yourself.
Okay, I want to call that the overturning poop cycle, because I've learned this word overturning for when things mix between layers. But let's go back to climate.
The biological pump is what it's generally called. But
the biological pump. Okay, we'll call it that. Please stay with us. We'll be right back to continue this conversation with Helen Czerski, author of Blue Machine, after a short break. Cleaning Up is brought to you by the members of our new leadership circle. So that is Actis, Ecopragma Capital, EDP Portugal, Euroelectric, Gilardini Foundation, KKR, National Grid, Octopus Energy, Quadrature Climate Foundation, and Wärtsilä. For more information on the Leadership Circle and to find out how to become a member, please visit cleaningup.live. That's cleaningup.live. If you're enjoying Cleaning Up, please make sure that you subscribe on YouTube or your favorite podcast platform and leave us a review. That really helps other people to find us. Please recommend Cleaning Up to your friends and colleagues, and sign up for our free newsletter at cleaninguppod.substack.com. That's cleaninguppod.substack.com. Let's talk about some of the specific ways in which climate is changed. There's non-climate ways, like killing all the blue whales, but there are, and we'll get to those as well. But in what ways is the climate changing that delicate system? So there's two
main abiotic ways, so non-biological ways. One of them is that you're just putting a lot of extra heat into the ocean. So the ocean's actually doing us a massive favor, because climate change is obviously an energy balance problem. Energy comes into the Earth system from the sun, it leaves as infrared radiation sometime later. The balance between the ins and the outs determines what you've got. So fundamentally, Earth's got some amount of energy, and because we've kind of bunged up the plug hole of it flowing away, the amount of energy is increasing. So where's it gone? Well, 90% of that extra heat energy has ended up in the ocean, which means it's not up here with us on land. So the ocean is doing us this enormous favor by sort of taking in this excess heat. And because the water has such a high heat capacity, like it takes an enormous amount of energy to heat water up by even a little bit, which is why a kettle is the most energy inefficient thing in your home.
I actually did the calculation based on the data in your book. It's 0.01 degrees centigrade. If you assume, I took the energy flow, you said that it was 90% of the 500 terawatts, and you multiply it all through, and then 70% stays in the top 700 meters.
Yeah.
So you can, and then the specific heat capacity of water, and I came to 0.01 degrees per year that the temperature would increase. Doesn't sound like a lot, does it?
No, I appreciate the back of the envelope calculation. I think the actual number might be a tiny bit higher than that, probably not much, but it's a lot of energy. The point is it's a lot of energy.
And if you wait until the end of this century, 70 years, it's 0.7 of a degree, right, which then frightens me terribly, because that's a lot.
Yeah. So if you stick that extra energy in, then the first thing it does, apart from heating up things that change biology, is you change the structure of the engine. Now, one of the ways that happens is that if that surface layer becomes more buoyant, then so the ocean has this kind of almost like a very warm skin that's up to 100 meters deep. So it depends where you are, but it's very warm because it's been heated by the sun, and so nutrients getting up to the surface and things like the overturning circulation depend on the layers not being so strong that they can't be mixed up. So if you have really, really, really strong layers, if you have what we call a strong stratification, if that layer is super, super buoyant, you need even more energy to mix up and down, and that causes a problem.
Sorry, question. Is it really a layer, or are we talking about a gradient? I mean,
no, so if you look at
thermoclines.
Thermocline's really sharp. So if you go, I spend time out at sea on research ships, and the standard thing you do is you send down a thing called a CTD that kind of measures a profile of temperature and salinity going down. So you measure the structure of the ocean beneath you. And it's really sharp. Almost everywhere in the ocean, you'll be up at the surface, the mixed layer will go down maybe to 50 meters, exactly the same temperature all the way down. Depends a bit on where you are and what time of year it is, but then the temperature will suddenly drop over, I don't know, it depends on where you are, but let's say 50 to 100 meters. And then it will keep going down for a bit, and then 500 meters down, it's just the same all the way down. Like, it's really sharp. You cannot look at a temperature profile without going, oh, there's a layer there. So it is, and it depends on the time of year, because when it's warmer in the summer and the winds are less, then it's a stronger, thinner layer. And when you get big winter storms and it cools down and you get lots of winds mixing things up, then it deepens and it's a bit harder to see. Anyway, so the point is that if you bung a load of extra heat energy into the surface, you make that upper layer more buoyant. So you make it harder for things to exchange across the layer, for warm water to be mixed down and for nutrients to be mixed up. But you also potentially change how currents are circulating. There's no boundaries in their system, right? The water's just moving. There's no wall to say it has to, apart from the continents, there's no wall to say it has to flow here and not there. So if you change the temperature distribution, because this isn't even, it's heating more in some places than in others, you're sort of shifting where these ocean fronts are, these boundaries, for example.
And so this is the concern about the AMOC, the Atlantic Meridional Overturning Circulation.
So the AMOC, which is often confused with the Gulf Stream, they're not the same thing. The Gulf Stream is part of the AMOC system. And my colleague, Tom Heap, I present this Radio 4 program, Rare Earth, and he says, AMOC's a terrible word. They should all get rid of it because it confuses everybody. But it's not the Gulf Stream. And, it's not a good word, but it's not a bad word if we just get everyone to understand what AMOC is.
Gulf Stream presumably is a big current that stays at the same level, and the AMOC is the bit that actually turns over and mixes. How am I doing?
So the Gulf Stream is wind-driven. So, and as long as the planet keeps turning and the wind keeps blowing, the Gulf Stream will keep going. The important thing about AMOC is the overturning bit, as you identified. It's where the warm water has moved south, it's cooled, and it's now salty enough to sink, and then you also get input from polar seas, and then you get cold, denser water that flows down and flows away. So this is really, so AMOC and the overturning circulation is really important for global climate, because that's what keeps Northern Europe warm. So the ocean's moving heat around. It's moving heat from the around the equator up towards the northern latitudes.
Now, there are those out there that would have us wake up screaming in the middle of the night because the AMOC is going to shut down. Do you wake up in the middle of the night screaming because the AMOC is going to shut down?
To be honest, I've got things to scream about before the AMOC shuts down. So there's been a lot of stories about this, and the general picture is that there are questions about whether the AMOC is weakening, because if it weakens and it potentially, then it might, it's just slowing down. How we'll have some changes, and if it stops, the worry is. So the definition of a tipping point in this context is not just that it will stop, but then if you then cool down the system, it won't restart. The big deal in climate science circles is that this is even on the table. The idea that this even might happen is a massive wake-up call.
It has happened before.
So then you look at paleo history, and so there's a lot of very clever paleoceanographers who have looked, for example, in sediments, and so they can see patterns of what's happened in the past. And we can see, I think Wally Brooker was the first person, a very famous American climate scientist, first person to sort of draw attention to this in the 80s or 90s, that there have been abrupt climate changes, that it wasn't just that it slowly got warmer. It seems to go quite quickly, not as quickly as what we're generating now, but on the scale of climate, you get a relatively rapid
thousands
shift.
of years. We're now doing a 100-year experiment.
Exactly.
Right.
Yeah. So that's where the idea of a tipping point came from, that there's some feedback systems where you stop the feed, you basically switch it from being a negative feedback to a positive feedback, and then you get this big change in the system. So the idea that is even on the table is a massive deal, just from the point of view of climate science. So I think we should take what's happening to those currents very seriously. There's a lot of uncertainty in exactly how what it means, right? We can't match up all of the paleo records exactly using current climate models. There's definitely a question about whether AMOC is slowing down. We also don't have data going back a very long way, but it's so serious if it happens. I mean, we really are talking about fundamentally changing what the planet looks like. So I don't worry about it happening, but I am worried that it's even on the table.
That sounds like a sort of preamble to an application for a research grant in some ways, because we clearly need to, if that's the situation, we need to do a lot more work.
That's true, but also it doesn't actually change the need for action, because even if the AMOC doesn't turn off or even slow down, the existing climate impacts are so bad that we already need to be decarbonising as quickly as possible.
So I have to get back to, if that isn't the thing that has you wake up screaming during the night,
right?
What is? I mean, if it's something that's vaguely related to oceans and climate, that is.
So it's the slow changes that creep up on us. So we can see it's these numbers where it doesn't look like a bit. I mean, we're nudging up on 1.5 degrees of climate change already, and that doesn't sound like a lot, perhaps, but it's not about the temperature going up by 1.5 degrees. It's the distribution of energy. It changes the shape of the engine, which is why it changes where you have floods and where you have droughts. And the thing is that our entire civilization is set up, just like the penguins, around the climate being predictable, that it rains here at this time of year and it doesn't rain here at this time of year. And if you shift that pattern, even if you just shift where it is, you've got this pattern of where things happen. If you shift it south by 100 kilometres, that's a massive deal. If you shift it north by 100 kilometres, that's a massive deal. And so the thing that bothers me is that these changes are already starting to happen and people are seeing them as a one-off. We've just had this horrendous hurricane in Helene in Florida, right, South Carolina, pretty much as we're talking. And those impacts, I mean, there have always been hurricanes in Florida, but if events like that stop being, a once in a 50-year event or a once in a 100-year event and become a once in a 2-year event, the world looks like a very different place. And that is what keeps me screaming at night. It's that it's already bad enough and it will get worse, but we can do something about it. So then the reason I get up after all the screaming, the reason I get up in the morning is because we are definitely still at a point where we can decarbonise and do something about this. We don't have to
now
give
you're on
into
my
this.
territory. This is the stuff I work on all the time, the cleaning up the energy system. And we can, and we must. I was very struck. There was an episode which my co-host, Bryony Worthington, I think it was about 3 or 4 episodes ago with Kelly Wanzer, and it was on geoengineering. And ocean acidification didn't get a look in. And that struck me as being, so acidification is not the same as climate change, but given that it's caused by fossil fuels, they obviously go hand in hand. So I was struck by something that's probably very familiar to you, but the kind of interrelatedness and the connection between different problems. So moving on from climate, how are we doing on ocean acidification?
So the corollary, the ocean acidification is also, the ocean's doing us 2 favours, right? It's taking up all the heat. It's also taking up a third of the carbon that's going into the atmosphere and just taking it out of the atmosphere where it does the most damage to the amount of energy in the planet. But that is not without consequences in the ocean. And so the question of how much carbon is going into the ocean is a big one. The reason it matters is that carbon in the ocean is linked to how acid or alkaline the ocean is. So the ocean, the pre-industrial era it's alkaline, about 8.1 on the pH scale. Now pH is a logarithmic scale, which means that a small number change means a big difference.
So I'm going to go back to school. 7 is neutral, but 2, if you go down to 5, it's much worse than going to 6, or going to 8 to 9 is much worse than 8.
So I think so for ocean, the pH of the ocean, it was at 8.1. It's now on average around 8.0, but that is a 30% increase in actual number of hydrogen ions floating around.
Yes.
So it's a very big difference. So, and this matters because all the little tiny sun harvesters on the surface, they've all got hard skeleton. About half of them have a skeleton made of calcium carbonate, and that requires an alkaline ocean to form in. Chalk, yes, is made from the skeletons of those little creatures. So So, and basically the building blocks, there's only two types of hard building blocks in the ocean. There are the calcium ones and the silicon ones. And the calcium ones predominate in the mid-latitudes where we are. And so if you make it harder for those things to grow their shells, you make a lot of things harder, right? Because that's the building block that lets all these things live, and you just take their building block away from them. And the problem, in a way, I think you're right that it gets less attention, and that's partly because that one is not really fixable. I mean, we just have to stop putting the carbon into the atmosphere. The solution is the same in a way. But once my actual research, the reason I study the bubbles is because if you've got a concentration gradient across the surface, so you have higher CO2 in the atmosphere than you do in the ocean, it will tend to go down through the surface. But the rate at which it goes down depends on turbulence and bubbles and mixing at the surface.
So your bubbles are absolutely key. That process of the ocean absorbing 1/3 of the CO2, fewer bubbles, less absorption, so then it stays up there and the whole thing can accelerate.
So that's right. So that question of how, so most of the ocean wind speeds aren't that high, depending on how you define high. But in places where you get really big storms, the last time I was at sea in November and December, we had on the average height for a period, the wave height was 11 meters and the wind speed was around 30 meters per second, which is like, I don't know, 70 miles an hour. Don't really work in miles an hour. Not conditions you want to be out in. But basically the surface of the ocean is blowing away. It's really violent and there's really good mixing across the boundary. So if you've got a concentration gradient, you've got a stonking great big kinetic, you're sort of giving it every opportunity to balance out, and that can speed up. So the question, not just for carbon dioxide, but also for oxygen, the speed at which it doesn't reach equilibrium. So how close to equilibrium can it get before that water packet moves away? So we're trying to understand carbon balances between the atmosphere and the ocean, and studying that is part of this.
It's really complicated because if we do get eventually more tropical storms, then we'll get a bit more mixing, but it's probably a secondary effect compared to the whole. So it's not going to be enough to solve the problem. Let's put it that way.
And actually the bigger problem is that there's a temperature factor in all of this, and that warmer water will dissolve less CO2 in it before it is saturated. And so if you're warming up the surface ocean, you're actually making it harder for the ocean to do that favor of taking in the carbon dioxide. So in order to predict we don't yet, the reason that I've still got a job doing this is that we don't yet have all the mechanistic pieces that let us be certain, if you change the storm track, if you change the structure of the ocean a bit, what happens next? And that's what we're trying to work out.
So there's plenty of other bad things we're doing. We already talked about removing the larger animals, the blue whales, and down to quite small fish. We've removed a lot, and that has an implication through the poo and other ways. There's also plastic pollution and noise pollution. I've got here stress levels amongst whales. Lovely stories in the book about whales' earwax.
Earwax, yeah. I mean, it's a shame. It's an interesting story in a way because it is such a beautiful story with such a depressing core. But yeah, I had the great privilege of going down into the Natural History Museum's stores, which is a wonderful place. If you ever get the chance, you should definitely go. And they have all these things in jars with scrawly handwriting. And I went down there to see these kind of sticks that are about the size and length of your thumb. And they've sort of got stripes going down the stick. And what this is whale earwax. And they have taken these out of dead whales, one from each ear. And the reason they're there is that whales used to be, they evolved from land mammals 60 million years ago.
The audience will just have to take it as read that they did used to have ears.
They did used to have ears, yeah. So they were land mammals with ears, structures like ours. So our outer ear is just part of our ear, right? Then there's a middle ear and an inner ear on the inside. And if an animal is going to start swimming around in water more, sticky out bits get in the way. They introduce loads of drag. So they got smaller, but that didn't matter because the whales were hearing through their jaws. So if you and I go swimming, we put our head under the water, it sounds different, not just because the sound is different, but because sound is not going down the hole in the ear. It's coming through the jaw.
One of your messengers.
Yes.
One of your messengers sound in the water.
That's right. So it comes in through the jaw and gets directly to the ear.
What did the earwax show?
So, and just to finish the story, so because they didn't need the outer ear, it grew over with skin and the earwax doesn't escape out, it just builds up across the inside of the ear. So what they did was they had these earwax plugs going back 150 years. They lined them all up, 2 museums. They've got a record. They looked in them for cortisol, which is a stress hormone, and they could get a hunt over global whales, basically loads of samples. So you've got 150-year record of stress in global whales. And you see the thing you would expect, which is that if when people are killing lots of whales at the height of industrial whaling, there's a stonking great big spike in stress. Not a surprise. It matches up, right? Industrial whaling and the stress matches up, except for the Second World War. Whale hunting went down because humans were busy trying to kill each other. Whale stress went up very sharply. And the explanation is it was the sound: guns, bombs, torpedoes, destroyers, generating sound, filling the ocean and making it stressful for the whales. And you can see it in their earwax.
Now,
I feel we're going to enormous rate here.
No, it's well, we are. I'm slightly speeding up because I'm keeping an eye on the time, and I could do this for hours, but the audience, they
might have other things to do.
Well, lots of them walk dogs whilst they listen to the podcast, right. or I don't think while they watch the YouTube. And there's only so far that Fido can walk, I'm guessing. Out there, though, in the audience, are a lot of people working on solutions. Now, my worry is that they will be, you've now called them, you've insulted them by saying they have this kind of stick man view of, smiley face ocean with two arms and a head. But they're doing things. And I want to ask, if we can do this fairly rapid fire, what are the implications of what they're doing? Let's start with offshore wind. What are does it kind of worry you, not worry you? What should they be worried about? What are the unintended consequences?
So the first thing is the biggest damage to the ocean comes from the carbon. So decarbonisation is a massive plus in the offshore energy. But wind turbines also have a few other effects. They generate a wind wake behind the wind farm above the water. They mix things up because you've got water flowing past these sort of poles below the water, which can change the nutrient distribution. And of course, you've got the other things around the wind farm, like how much fishing there is. If you have a big wind farm, fishing vessels tend not to go there. And basically the answer of whether that is a good thing or a bad thing is that it's definitely not as large as most other things that are going on. It's quite hard to separate out that signal. And it's very dependent on exactly what the site is, but I am not worried about that. I get especially in shallow places like the North Sea that have already got lots of ocean infrastructure, the wind turbines are not, compared to the benefit they have, I think any potential detriment to the ocean is very small, but those studies are ongoing. People are looking.
And what about noise? Are you worried about the noise? Machinery rotating, those sorts of things. Lots of boats going to and fro doing maintenance. Noise
in the ocean is big. So with a wind farm, the biggest source of sound is the pile driver to get the monopole into place. And people are looking at ways of shielding that. None of which are very effective just yet, I think. But
using bubbles.
Some of them use bubbles. And we're working at UCL. I'm involved in some projects to try and design better ways of doing that. So I think we can work that out. And of course, a floating wind turbine doesn't have any of those problems.
Well, it still has a float. So I was going to get onto floating. It still goes underwater. You still have a great big leg that balances it. And potentially there are visions of the future where the floating wind turbines are on floating islands and they include industry and they get hybridized with solar and we move, lots of stuff offshore. Does that worry you kind of long-term, short-term, or frankly, not at all?
It does worry me because I think there's a critical question before, and we do this on land routinely, but we don't, so at least some of the time, we don't do it very well in the ocean, which is ask, what is the ocean already doing in that place before we got there?
Oh, but it's just water, right?
No, that's the whole point. And you are being very mean. But the whole point is that it's already doing stuff that benefits us. So before you can't assume it's a blank slate. Like if there is one thing that I would like, if I could sort of wear on a t-shirt and wave as a banner, it's the ocean is not a blank slate. It's a living, it's the equivalent, it's got the complexity of a living organism. So treat it like that. Right? Don't go in with something that, I sometimes slightly rudely describe as the Donald Trump and the bleach attitude, like bleach kills germs. I have germs I don't want, therefore drink bleach, right? That and with no appreciation that there's a whole system there which does not respond so well to bleach and there are complexities involved. You definitely shouldn't drink bleach. And I think we just need to make sure we're fully appreciating what the ocean is doing for us before we make those decisions.
Yeah, I think that suggestion came more out of the entertainment industry than anything else. So I mean, there's sort of describing wonderful structures in the ocean probably is at the moment more entertainment than actual reality.
Yeah, but I'm sure there's some people trying to raise venture capital to do it. So,
I'm sure that's true. What about high voltage DC cables, of which I'm a big fan, so you have to be careful here.
Well, unfortunately, I don't know a lot about them, but I think of all the things that might damage the ocean, I think these are probably less damaging to the ocean itself, because the track of these cables are actually quite small. They sound very big and chunky, but I've seen the interconnectors, the North Sea interconnectors, and they're kind of like, I don't know, a few centimeters across the core. So I don't think that and we already run internet cables, optical fibers across the ocean. So I'm not too worried about.
These would be buried, I'm guessing. I mean, most of them will be buried most of the way. So they don't get trolled up or attacked by Russians. Yeah,
and you get scour. It's quite complicated to put things in the ocean. And that is the one, I mean, so you'd have to run it along the shelf. But of course, sediment builds up and scours out, and it's not as static down there as everyone thinks. So as long as you can deal with that.
We do have a few hundred years of knowledge about cables. I mean, not a few hundred, but 150 or something like that, including the
So
cables.
I'm less worried about that.
Less worried about that. Good, excellent. Because I think that they are going to be a much bigger piece of the future than most people perhaps listening to this realise. And they're just such a good way of moving electricity and exergy around.
If they stop people trawling, I'm all for it. I think bottom trawling and dredging is terrible. Anyway.
Well, let's get on to then ocean mining. You write in your book about these polymetallic nodules. I mean, it's great on this vast empty space, which we know more about the moon than we do about the bottom of the ocean.
Don't even get me. That is a whole other rant, that you're not allowed to say that. That's the other message. If you go away from this podcast, do not compare the moon with the deep ocean. The moon is very nice, but it's been dead for billions of years and it's not changing. And the ocean is the exact opposite. And every time you compare the two, you make it sound like the deep ocean is like the moon.
I had to get that one. I knew it was one that would annoy you.
I've got a proper rant about that.
I knew that was one that you were.
But the nodules. Yeah. So the thing about the nodules is it's a very slow moving system. These things grow over millions of years. It's not a renewable resource, and we don't know what they're doing. And the recent discovery of deep ocean oxygen was a really interesting. That's just an example of one thing we've discovered that we didn't know.
Let's back up just a little, because I didn't know that we discovered deep ocean oxygen. How do these nodules, they don't just get kind of ejected from underground, underwater volcanoes.
No.
They grow in situ and they do things electrically. Is that what you're saying?
Yeah. So basically they grow, the ones people are talking about grow in very specific areas of the ocean. It has to be between 4 and 6 kilometers deep, and you need an extremely slow rain of stuff from above. So basically almost nothing falling. You need a bit.
Or they get covered up.
Yeah. So, but they need a little substrate to start. So quite often it's a shark's tooth or some other little solid thing that fell down from the surface. And then over huge periods of time, minerals start very slowly to accrete on top of it. So you can get people call them sea potatoes, about the size of it. So one that's about the size of my fist is probably 2 million years old. That's how long it's taken to form. And they just sit in a single layer at the top. They're kind of spread out all over the surface. No one really knows why they don't get buried at all. They seem to kind of stay at the surface somehow, and occasionally they get turned over by a sea cucumber or something like that. Things do live on them. They have extremely weird ecosystems with very odd creatures, not very many, but very odd and in extremely high diversity. So they're very strange, environments. And yes, so people have talked about mining them in the 70s. They're having another go now. And into the middle of all of that, one of the things that the mining brought with it is a requirement to the International Seabed Authority, which regulates this, although it's not really set up to say no, it's set up to say yes, but that's a whole other thing, has a requirement that there's an assessment of environmental damage on any mining activity. And so the companies that have exploration, not extraction licenses, they're having to fund a lot of biology so that some biologists go in and look at what's there. And one of the companies that is at the forefront of pushing for deep sea mining, the metals company, one of the studies it funded involved putting these little umbrellas down over the surface. So it's like you trap a region like a bell jar. Yeah, you plonk it down, and then you monitor the gases inside, and everything on the inside just goes on living, and you monitor what gas is there, and particularly what oxygen is there. And it was always assumed that these experiments were for monitoring consumption of oxygen, because you can tell how much is living there by how much oxygen is consumed. But what these scientists saw was that oxygen was being produced. And then they went back and looked, they thought this is a bit weird. And they went back and they actually tried to publish in Nature a few years ago. And I know from colleagues at the same institution that Nature said to them, look, this is really interesting, but you cannot publish unless it's bulletproof. So they were made to go back and do more studies and read, they did a series of very nice studies, and this is absolutely robust.
So it's robust.
And what they found is that where there are nodules inside these bell jars, the oxygen goes up. And it varies.
Now I'm scared because if there's oxygen going up, there's presumably hydrogen going up too, or maybe being dissolved into the...
I think the hydrogen... It's an interesting question. I would think the hydrogen matters a bit less because it's not biologically active.
It's just that
it might be.
I have a whole audience that's attuned to the hydrogen and they'll stop walking. They'll stop walking Fido and turn the volume up.
So the mechanism that they think they could reproduce this on land was that there is electrolysis going on. So because these are polymetallic, at different points on the surface, different metals are exposed, and the voltage difference can be big enough that you can get electrolysis. But what they found is it seems to be patchy. It's not clear whether it happens for every nodule. It's not clear whether you need some other conditions to be right. But something definitely is generating oxygen, which is a massive deal for our own, because we just assume the only source of oxygen is at the surface where there's photosynthesis. And, so any oxygen you get down there, because everything down there breathes oxygen, needs oxygen, it must be carried down through these overturning currents. And so the idea that there is even potentially, that's a massive biological thing we just didn't know about. Maybe we should find out what it's doing before we go destroy it.
Thermodynamically, because it must be extracting energy from the flow of water. Yeah. Because, there's energy. If you're electrolyzing, you're using energy. It's got to come from, there's no light down there. It must be coming from chemicals.
All these questions, yeah.
Okay, final one of what people are trying to do, carbon removal. Using the oceans, just sinking a whole bunch of...
and you picked that one for last. That's another whole podcast. This is something that I do see quite a bit of because it's carbon related. So yes, people are proposing lots. It's marine CDR, MCDR. People are proposing lots of ways to try and get... So the ocean already takes up a lot of carbon, and these people say, we can, if we just get it to take up a bit more...
We'll scatter some iron filings and there'll be a big algal bloom and then it'll sink and it'll all go down and just to this blank space that doesn't really matter.
So the iron fertilization was debunked 20 years ago and it is still debunked now, but there are still people proposing it anyway. But so now there's all these different methods and there are a few difficulties with this. One of them is that the carbon up, they all rely on, you do something to the ocean and then that packet of water drifts off with a bit less carbon. And then at some point later, it has to take carbon up from the atmosphere. So the point at which you do the thing is not the bit where any carbon goes in from the atmosphere. And if that water packet then goes downwards, it never touches the atmosphere, it never does anything. And also there are timescales here. So how long does it take potentially to have some exchange? It's not like you plant a tree and you come back 20 years later to see whether your tree is still there. Your water's it's off, it's drifting on the currents of the ocean. The only way to predict whether or not there's going to be any exchange is to run models. And at the moment, we don't have models that have enough detail to be certain about how much carbon will be taken up. And there's a lot of talk about methods that if you scaled them up would have huge ecological and social consequences. And it's just assumed that scaling up is easy. And there's a difference between something working technically and being able to scale it up enough to make a difference.
And presumably it takes a whole bunch of nutrients. It doesn't just take the carbon out. It'll take a whole bunch of nutrients. You'll end up with a sort of floating desert of nutrients.
So if
absorbing carbon at some point if it gets to the right place.
So most carbon scientists think that the biological methods they're just not going to do anything, partly because of things like that. But the other partly because the ocean just cycles carbon really quickly. But the methods that have more the only ones that have any credibility, I think, they'll all be emailing and being cross at me, but that's fine, as long as they produce robust arguments, is the chemical and physical methods.
So the DOC, direct ocean carbon removal.
Yes, and my partner David Ho hates that because DOC is a technical term in the ocean for dissolved organic carbon. So if you say DOC, it's really easily. So he thinks what does he think you should call it? Direct ocean removal or something, I think.
So SMRs is steam methane reforming to make blue hydrogen or to make hydrogen from natural gas, but it's also a small modular reactor.
Yes,
we're just going to have to live with a little bit of
But in the ocean, they are both anyway. It confuses everyone. Yes, so the methods that seem more likely to potentially work involve enhancing ocean alkalinity. So putting minerals into the water because that shifts the carbon buffers. So then you have a deficit of dissolved carbon dioxide and then you might get some in from the surface. And we're still, the science to work out whether that even might work is still being done. So it's not a silver bullet. There are large implications for how you do it. And the thing is, in a way, it doesn't matter. This technology is not something we need to deploy now, because if you've got spare money and energy now, it should be going into decarbonising, because none of this is going to make any difference unless we have really substantially decarbonised. So I think doing the research now is really important, but deploying this as an offset is just stupid unless we are almost completely decarbonised. And you're talking about last
I couldn't agree more. The thermodynamics of allowing CO2 to mix to 420 parts per million and then having to do huge amounts of work, whether it's in the air or in the ocean, to separate it, it makes absolutely no sense.
Yep.
So we should stop burning stuff. We are almost exactly out of time. Let me ask you one final question. If you had one ask, we haven't talked about your canoeing. We should, I'm not sure if that will be the ask, but
they can read the book.
read the book. There's lots of wonderful stuff, stories about canoeing around Hawaii, and also about reconnecting with the oceans, which is something that most cultures have lost, and in Hawaii they hadn't. And it's really very nice. They're very nice segments of the book. I enjoyed those thoroughly. But let's get back to one ask from, we have a very influential audience. But just in general, what would you like to see happen with your knowledge and the topics that we've been talking about around energy and climate?
I mean, apart from rapid decarbonisation as quickly as possible, which we can take that as read.
You've kind of already asked for that, but you can ask for it again. But,
I think
else.
People should take the ocean seriously as a massive benefit to our civilization, and they should look at it and sort of appreciate that just because it's distant doesn't mean it's irrelevant, and we should stop treating it as a void. More than anything else, I think it just should not be possible in the future for our civilization to treat the ocean as though it's this magic place called away, or it's empty, because they are not true.
So I've been teasing you a bit throughout by saying, well, it's just empty, and I know that that's a hot button issue, but what would you say then to people who say, I absolutely agree with you, and that's why we need to put a value on it, because that's the only thing that our societies care about?
Right. So that argument, I think it's a question of how you measure your value, right? Because the assumption when you say we're going to put a value on it is that it's going to be a financial value. Whereas if you look at a value I think we've got three life support systems. We've got our own body, we've got our planet, and we've got the infrastructure of our civilization. And what's the value of your life support system? I would say it's pretty high. But can you put a number on it? I mean, for technical reasons, we often do. Or can we put a financial number on it? So I think we should put a value on the ocean, but that value should not only be financial. It's an integrated system. It's not something where you can... This is a game of Jenga, right? If you take out enough blocks, then the whole thing falls down. And the measure of value shouldn't be, can we take out this block and the system doesn't fall apart? The measure of the value should be, how do we maintain this system so it never falls apart?
But let me just push, because I agree with you, right? Because the moment you say, well, this particular species of krill is worth $42 million, then somebody can say, well, I'm building a super island and I'm going to make more than $42 million. So therefore you just do and I'm going to pay a lot of taxes. And so that's it, we're fine. So it's not a financial value, but are you arguing that everything is of infinite value? Because that's a difficult argument as well.
I think that's right. I understand that there are trade-offs, but what I think is that you should consider the whole system when you make your trade-offs. I work for various strange reasons that in my personal history in a department of engineers who are very nice. I'm in the Department of Mechanical Engineering at University College London. And it's actually very useful for me to watch engineers think. But what I have realized over my years there, and these are very, very bright, very intelligent, well-intentioned people, is that we have trained our engineers to look only at a very narrow, to constrain a problem down, to turn A into B, and then let them solve that problem.
Reductionism.
It's reductionism, right? To an extreme degree. That is how we train our engineers. And almost all of our climate problems, when you really look at it, have come from that attitude. I'm going to make a local solution to a local problem. So I think what the problem with the financial thing is that it gives people a way to do exactly what you just said, to turn a local solution to a local problem and ignore the rest of the system. And we can't allow that.
So on that note, this reminds me of a previous episode with an engineer, a great engineer, David Seaborn, Professor Seaborn from Cambridge. And the episode was called thinking in systems. So
Hooray, the engineers are finally getting there.
there is a good understanding that we need to think in systems.
I hope so. And actually, I mean, one of my teaching role at UCL at the moment is to put sustainability into the engineering curriculum. It's a really interesting intellectual exercise. Like, what is it what are the simple messages that I want trainee engineers to know? And that won't terrify them. They're not going to do an environmental science degree, so much of it is just how you think about the world, and not in a reductionist way.
I want all chief sustainability officers to be fired. As soon as you have one, you offload all your problems onto the CSO, right, and the CEO is off the hook. Yeah.
So what we're trying to do in this, I mean, the point of what I'm doing is to embed sustainability into every module, okay, and that, like, you've got to see the world differently. And it is a thing, like, how do you put a value on seeing the world differently? But unless you do it, this life support system we have is not going to survive.
Very good. Helen, it sounds infinitely valuable to me. Thank you so much for spending time with us here today.
Thank you. It's been fun.
So that was Professor Helen Czerski, physicist, oceanographer, Hawaiian canoe paddler, and of course, author of Blue Machine. And we'll put a link in the show notes to, of course, Helen's book, as well as to the episode that I mentioned with Professor David Seaborn. That's episode 107, Thinking in Systems. And as always, I'd like to thank the team behind Cleaning Up, as well as the members of the Leadership Circle. So that is Actis, Ecopragma Capital, Euroelectric, Gilardini Foundation, National Grid, Octopus, Quadrature Climate Foundation, Energias de Portugal, and Wärtsilä. Please join us at the same time next week for another episode of Cleaning Up. If you're enjoying Cleaning Up, please make sure that you subscribe on YouTube or your favorite podcast platform and leave us a review. That really helps other people to find us. Please recommend Cleaning Up to your friends and colleagues and sign up for our free newsletter at cleaninguppod.substack.com. That's cleaninguppod.substack.com.